Welcome to another lecture of the series of modeling and analysis of DC-DC power converters. So in the last lectures we have analyzed the different so we started with linear regulators, the linear power converters. Then we moved on to switch mode power converters, the allowable states, the allowable connection of the components by using a switched power converter or a switch device like any transistor operating in the cutoff and saturation region. And then the basic topologies of DC-DC converters like buck boost and buck boost converters, their continuous mode of operation, discontinuous mode of operation, then the critical inductances, the minimum load across any boost and buck boost converter. Then we went on to DC-DC current converters, current boost, current buck and current buck boost converter, and we went on then we moved on to derivation of higher order DC-DC voltage converters using the current converters. So now we'll move on to another topic of isolated DC-DC converters. So as you know that the word suggests isolation means all the topologies which we have seen till now, the negative terminal of the supply is directly connected to the negative terminal of the load. Say that we want to implement any of these DC-DC power converters for EV charging applications. So as the converter has no isolation, there may be a risk of a shock if in case there is no isolation, or if by mistake, say the earth of the vehicle is not connected to the is not grounded properly. So the input side negative terminal is directly connected to the charger, which means that it may be contact with the body of the vehicle or the body of the charger. In case by mistake any user touches it, then he will get a very deadly shock. So in order to prevent the risk of short, and so there can be multiple reasons to it. There might be some negligences due to cost cutting at the converter end or at the charger end, or maybe some failure of the earthing terminal of the supply port. There can be many reasons. So in order to ascertain safety irrespective of all these negligences, it is better if our power converter itself has isolation. So that's why there is a need to have isolated DC-DC power converters. So, and also while designing any product, we have to be compliant to the different safety standards posed on by the government. So that's why there is a need for isolation. So isolation is used to reduce after fault damages and accidents in the applications. So also the advantages of isolated DC-DC converters is that we can get high step up or step down as per our application. It will also help to protect our sensitive loads or sensitive electronic components like from different incidences like lightning strikes, so that there will be a path for that excessive surge to move to the ground instead of coming in contact with the metal body of the converter or the load. So in order to help this, the components like MOVs, lightning arresters or surge arresters are used. Then another advantage of isolated DC-DC power converter is that so what's the electrical circuitry that will give isolation between its input and output? That is the transistor. So transistor is a classical example of isolated of electrical device which provides isolation. This is a simple transformer. So this is V1 or V primary, I will denote. This is V secondary. This is number of turns in primary, number of turns in secondary. This is the primary current, this is the secondary current. So say Vs is the induced voltage, induced secondary voltage, and Vp is the supply voltage. So Vp is a AC voltage. So it can be a single phase or a three phase supply. So 230 root 2 into sine of omega. Omega is 2 pi f, 100 pi t. This is the primary supply voltage for a single phase supply. So if you draw the equivalent circuit of a transformer, so it will be like this is VP, this is IP. So a transformer draws a current. Very first thing is the principle of induction of the voltage across its secondary or output terminal is due to electromagnetic field, which means the core on which the transformer is wounded, that has to be magnetized. So the electrical component that is representative of the magnetizing current, or the current drawn from magnetizing the core, is denoted by a very big inductance known as Lm, and this is the magnetizing current Im. Then further, the other components are, so here you can write as Rm. This is the magnetizing current. Then so basically so instead of drawing it here, I will shift this portion here. So I'll draw the transformer core. So this portion is called as core. This is a EE core. These are EE cores. So say the primary is winded. This is the NP, and this is the secondary, this is the primary, this is NS. So what happens is, this is the primary voltage VP and this is VS. A primary current AC flows through the circuitry, electromagnetic means alternating current, which will result in flow of flux through the core. This is the flow of the flux. So basically what happens is, if we draw the Faraday's law of if you use a Fleming's right hand rule, so there will be some flux will be flowing like this, and this will be confined to the core. So the useful component of the flux, which is used for induction of the secondary voltage, is the useful flux, and the other flux is the leakage flux. So the component that used to represent this leakage flux is this leakage LL1, that is at the primary end. Similarly, every inductance has every wire has a resistance. So let's say this is R1. Then some current is drawn to magnetize the core. So that current is represented by this. So it can be L mu, this can be R mu, or this Im or I mu. Then what happens is, then comes the turns. Similarly, secondary voltage is directly induced, so there is no magnetizing component present. This is the dot convention. This is R2, this is LL2, and this is I2, this is VS. This is NS, this is NP. If we want to represent this component, if you want to get rid of this transformer, so it is like this. So usually this RM component is very high. So basically this is the no load loss component, and the other one is the magnetizing component. No load loss means say that there is no load at the transformer at the secondary end. So no load component, the transformer will draw the current for two things. One is to magnetize the core, which is always fixed for a given transformer irrespective of the load. Second is the load component of current. So basically, so here you can write it as reflect. Okay, that will draw later. So let's say there is no load across it, so no load current will flow. So the no load current is typically very less. So basically this Rm is representative of the, this is I naught and this is I mu, and this you can write as I naught. I will write it I naught. Oh sorry, not I naught. I am, I'll write, this is I mu, this is I naught. This is R naught and this is L mu, I will write. This is R naught or J X mu. So typically we can ignore this R naught because the current is very less, which means that the inductance, the resistance R naught is very big. So this is Vp, this is RL1, this is L1, this is this current is J, we'll write it as Im. Then if you want to get rid of this component, you have to transfer this component to secondary to primary. So what you do is, if you want to transfer this component from secondary to primary, you have to the voltage and current terms you have to multiply by the number of turns, and for impedance and for the quantities which has the units of impedance or resistance, that has to be multiplied by square of the number of turns. So basically what you do is V1 Vp by Vs is Np by Ns. So let's say, so Vp equals to Vs into Ns by Np, or this you can call as Vs dash. Vs dash is the component across this. So what we'll be having is, this is RL2, LL2, and this is Im, this is Ip, and this is Is dash, and then here we have Vs. This is the load. RL2 dash, LL2 dash, Vs dash. So where RL2 dash is RL2 into what? Ns by Np whole square. Similarly, XL2 dash is XL2 Ns by Np whole square. Similarly, Vs dash and Is dash is Vs comma Is into Ns by Np. These are transformed quantities. So say that this is a single phase supply. So say omega is 100 pi radians per second, and we know that the voltage induced across transformer E is 4.44 into B into, so this relation of the voltage induced of transformer is 4.44 into B. B is the flux density, that is flux per area. So B into A cross section, 4.44 into B into F into B into A into F into number of turns. Why? How this formula is derived? So because E is d phi by dt into N, that is d phi by dt. So let Vp is Vm sine of omega t. So Vp, let's say Vp is Vm sin omega t. So the flux induced, say phi peak or phi m sine of omega t. So it will be n into phi m into omega, sine becomes cos omega t. So you can write as n into phi m into 2 pi into f into what? This into cos of omega t. So therefore Em becomes what? 2 pi phi m into n into f. But you know that the flux density is flux per area. So you can write as 2 pi b into a into f into n. So it becomes what? This is Em and this is E RMS. So Em is 6.14 into B into A into F into N. So therefore E RMS is what? 6.14 into root 2 into B A F N, which becomes 4.44 into B into A into F into N. So what happens is the transformer size is inversely proportional to the operating frequency. This is the F operating frequency. And you know that in the expression, even in the expression of critical inductance of converters, or say normal, so in the previous lectures we saw design of converter parameters. First we saw how to design L and C for a given delta I and for a given delta V naught. Then we saw what is a critical then we saw what is the minimum load on each of the on the boost and buck boost converter. Then we saw the critical inductance for the buck boost and buck boost converter. In all the expression of L, you found that L is inversely proportional to F. Similarly here, because transformer works on the inductor principle, here also the transformer size depends on the frequency. So if you have application like a so application is a mobile charger, which is a 12 volt up to 2 ampere charger. Then what we do is, this is the supply, I did a mistake, I should draw more terms here. So this is 230 volt RMS. So after this we have a diode bridge. And these two terminals are brought out. This is B and this is A. So after A, between A and B, you can have a filter capacitor and then a box. Again a filter capacitor, means the capacitor which maintains the voltage. So here that is 12 volt, 2 ampere. This is the converter. This converter can be a linear regulator or it can be a switch mode regulator. So here again what happens is, say this transformer is 230 to say 24 volt. So NP by NS is becomes 230 by 24 types of thing. And what is the voltage across VAB? So VAB has a voltage of, say it is 24 volts till here it is 230, it is 24 into root 2 because it is the capacitor will charge to its peak value. Now into 0.85, this term into 0.85, but it is the loading factor. So here what happens is the power converter, the input is this value, this is the V peak, VAB, and output is 12 volt. So if you are using any DC-DC converter, then you should have a say we are not using linear regulator, we are using switch mode regulator. So you need a buck converter logically. Now here what happens is this whole application, the transformer, this is the transformer. Transformer is very bulky and lossy. So because the operating frequency is switching, the operating frequency. So here this is a FSW and D. Because here the operating frequency is the power frequency, so the size of the transformer will increase. Then there will be losses, eddy current losses, hysteresis losses. So in order to rectify the eddy current losses, we mitigate the we reduce the eddy current losses by using laminated core, means stacking multiple plates of the iron material or the core material one upon the other. So, and also here in this case the core is the iron or the ferrite core, the iron material core. So it has its own flux density. So what happens is the transformer becomes bulky, there are losses. So if you use a laminated core, it becomes very bulky and lossy. So to get rid of it, why not to incorporate this transformer inside a power converter which operates at switching frequency. So the transformer operates at FSW rather than 50 Hertz. In this way, what will happen is the size of the transformer will be reduced. Why? Because so it's about the number of turns. The number of turns will decide the value of the voltage induced across its secondary for a given supplied primary voltage. But the size of the transformer are decided by many factors, and one of the very important factor is nothing but the operating frequency. The requirement, because the requirement of the magnetizing inductance and all will depend on the core material type. Say iron core, ferrite core, then will be eddy current losses and hysteresis losses. So hysteresis losses are proportional to frequency to the power n, and eddy current losses are proportional to frequency square. So let's say if FSW, if F increases, what will happen is the transformer, the ERMS will increase, the induced voltage will increase, the losses, which is nothing but the hysteresis and eddy current, will both increase. So now we want to operate the same transformer with the we know that by using high switching frequency, the size of the transformer will be reduced. Why? Because the weight to. So here we are discussing the working of a multi-winding transformer. So here we have multiple windings. Here you can see, and these are the relation. We are using the MMF balance. MMF balance is sigma n into j, or sigma n into I is 0. So this is the case for an ideal transformer. For a practical transformer, it is like, see, we are giving a square wave excitation to the primary winding. And this has 0 average value. Why? Because the inductor core will saturate. with the average value. And then in secondary we have multiple secondary windings. This is I2 and this is I3. This is I1 dash, and this is IM, this is LM. So what happens is, if I2 and I3 both are 0, then I1 dash will also be 0. So in this case what happens is, this is say I1 dash is called as the reflected component of the primary side current, which is due to the secondary currents. So here I1 is IM plus I2 dash, and I2 dash is what? I2 into N2 by N3 plus N2 by N1 plus I3 into N3 by N1. So this is the case. So what happens is, in this case what happens is, if the converter has no load, say that this transformer is a part of the DC-DC converter. So if we say example of any converter, say we have a buck converter. A buck converter, there is a switch, there is a diode, there is an inductor, and there is a LC filter. So if we just plot the voltage across the diode, so how will be VD? When the switch is on, it is reverse bias. So the voltage across the diode VD is, this is plus minus, is what? Minus Vin. So it is minus Vin. When the switch is off and it is 0, then the voltage across the diode will be this. So what happens here is, we can break this section and we can insert a transformer here. We can have a transformer here in place of this voltage. So this transformer, this voltage source can be applied here. So basically in this branch we can insert a transformer. So if we just plot the BH plot of a practical transformer, what we will get is that this is the saturation, here is the saturation, and this is the from here, this is the case, this is the saturation, this is B and this is H. So instead of H you can have IM, because H is a function of current, and the current drawn by the transformer is nothing but for magnetizing the core. Say that H is the magnetic field intensity, so it will draw some current, so that is necessary for production of the electromagnetic field. And B, or you can write, is a part of integral VL of dt. Now why VL of dt is because say it is V1 of dt. This is V1. So if you have so basically LM is an inductance, so VLM is equals to LM DIM by dt for I2 and I3 equals to 0. So what happens is, the total primary current drawn is nothing but used for magnetizing of the core. So if we apply the volt second balance, so it says that if the volt second balance is true, then the core, transformer core, magnetizes for the one time interval for some time and demagnetizes for the other time. Means if we see integral of VLM dt 1 by Lm is equals to Im. So if this we are considering as the y-axis, and if this is x-axis, so y equals to Lm into x. So this slope is nothing but the magnetizing inductance. So the transformer can operate in these regions, quadrant number 1 and quadrant number 3. So 1 and 3 are the operating regions of the transformer, and the slope of BH curve gives the magnetizing inductance. We already know that the slope of the BH curves gives mu, so mu is directly proportional to Lm. This we can write, and slope is directly proportional to Lm. So the magnetizing current Im is proportional to the magnetic field intensity inside the core, and you can say that the magnetic field intensity, that is nothing but H, or flux phi, because we already know that H is proportional to phi, and B is proportional to what? MMF, which is Ni. We already saw there was a relation between B and MMF. P is mu Ni. So the relation between, so here what we can say, how to prove is that B by H, which is mu, should be equals to, so we already saw that H is proportional to, so we say that H is directly proportional to I, so therefore H equals to some K1 into I. Similarly, so if in denominator we have I, so we have to have a sum term in the numerator, so that the ratio of this term by I equals to mu. So H is proportional to Ni. So this formula phi equals to mu NaI we can write as what? Mu A by L into MMF. So phi to MMF. This B is proportional to phi and H is proportional to MMF, or that is I. So MMF. So the ratio of phi by MMF is proportional to mu. Is proportional to reluctance, and the reluctance is proportional to mu, inversely proportional to mu. So this relation holds true. So magnetic field intensity or the flux is governed by the magnetizing current behavior, which means that if Im is small, the flux density Bm is directly proportional to Im, and if Im is very large, there is a marginal increment in Bm due to the reduced mu in saturation region. So presence of magnetizing inductors explains us that why transformer does not work in DC circuit, because here again volt second balance should be satisfied. So volt second balance should be satisfied. So I'll just so here I'll write conditions for a transformer or transformer is like, this is the shortcut for abbreviation for transformer. Condition for a transformer to operate as an inherent part of any DC-DC converter. First part is that the voltage second balance should be satisfied. So it means that Vm into T on should be equals to Vm on into T on equals to Vm off into T off, or 1 by Lm integral VLMF dt from 0 to T switching should be 0, because here T is T switching. The inductor is operated at the switching frequency, not the power frequency. So what happens if there is a DC component here? The volt second balance is not satisfied. That is, the magnetizing inductance has zero impedance, where here you can write as Xm equals to J into Lm, and thus the transfer primary will be short circuited, which will not allow the transfer of power to the secondary side. So another requirement of transformer is that we have to reduce the IM, that is the current drawn for magnetizing the core, because that basically the transformer draws more current. The transformer draws current for two things. First is for transferring the power from primary to secondary. But what is the means? How does a transformer transform the power from primary to the secondary with isolation? Is that based on the electromagnetic induction, based on the principle of electromagnetic induction. For that electromagnetic induction, the transformer needs to first magnetize the core so that the flux flows through the core, and thus due to this rate of change of the flux, the EMF is induced at the secondary, and thus as EMF is induced and the circuit is closed, we get a current. So thus if there is a current, which means that power is transferred from primary to the secondary with isolation. So typically we want this magnetizing current to be very small. So for the rated power transfer, the magnetizing current should be minimized. So to minimize IM should be less, or the value of Xm or Lm should be very high. It would be practically very high. This is one requirement for using the transformer to operate as a part of a DC-DC converter. This will result in IM will be very less than I1 dash. So what happens then, what you can write is that I1 is almost equals to I1 dash. So if IM is negligible, I1 equals to I1 dash. So this is the assumption. So that's why it behaves as an ideal transformer. Now volt second balance. Volt second balance is that IM of T equals to 1 by Lm integral 0 to T switching Vm of T into dt plus integration constant, that is Im of 0. This is what we have written. So this is the volt second balance. So it means that when a steady, so this is the initial or residual flux, you can say residual flux, or the flux present in the transformer initially. So what happens is that during steady state, using volt second balance, what happens is that the average value of Im of t over a time period of the entire switching cycle is 0. That is, what is the average value of Im? Average value is 1 by t switching integral 0 to t switching Im of t dt. And what is this? Sorry, using the volt second balance, the average value of V should be 0 for a cycle. So Vm of t, Vt switching, what is that? 1 by t integral 0 to t switching Vm of t dt. That should be the case. Then the transformer core will not be saturated. If this is not valid, what will happen is that, let's say this is equation number 2, this is equation number 1. If 1 and 2 are not valid, then what will happen is that, so what will happen if the equation 1 and 2 will not be satisfied? So then Im of 0, so for start of each cycle, isn't the same. That is, Im of t1 is not equal to, or you can say less than Im at, okay, t switching, or here I can add 0, is less than Im at 2t switching, and so on, which means that the waveform of Im will be like this. This is 0, this is t switching, this is 2t switching, this is 3t switching, this is Im, and this is Im of 0, this is Im of t switching, this is Im of 2t switching, and so on, and its average value is keeping on increasing. So this will saturate the core. The core will be saturated. So ideally, Im of n into t switching should be equals to Im of n plus 1 into t switching, where n equals to 0, 1, 2, and so on. That is, at the end of each switching cycle, the value of Im should be 0. Or you can say that Im of 0 should not be equals to Im of n into t switching, which is equals to Im of n plus 1 into t switching. So only the initial flux, which means that it is like this. This is Im of 0, and it goes on. So the average value is like this. This is also valid. So this phenomenon of build-up of flux is called as flux walking, and thus the core will be saturated. So in this case we neglected the leakage inductance, but if we consider leakage inductances or inductance LL1, then it will be like this. This is the copper loss component, this is Ln1, this is RL1, this is the big Lm, or I can write Xm, this is I1, this is Im, N1, and this is I1 dash, this is I2, and this is I3. So this LL1 causes, what does it causes? Switching loss, and it will result in peak switch voltage or voltage stress across a switch increases. It will also result in the low cross regulation. So this was the analysis of a transformer. So what we assumed is that we started our lecture with the basic fundamentals of a transformer, the equivalent circuit of a single phase transformer. What are the core loss component, what is the magnetizing component, no load loss, the no load current drawn, then the equivalent circuit referred to the primary side, then the construction, the flow of flux through it. Then we started with the basic Faraday's law of pneumatic induction, the equation of the RMS value of the transformer. We saw that the EMF induced is directly proportional to the flux density, the area of the cross section, frequency, and the number of turns. So also we saw that the transformer size is inversely proportional to the switching frequency, because given that the power to be transferred by the transformer is same for two switching frequencies, the requirement of the magnetizing current for both the cases are different. And inductances, we already saw in the DC-DC converter that inductance is always inversely proportional to the switching frequency. So as the switching frequency increases, the requirement of the inductance will be reduced. So the transformer size will be reduced. So we saw that the usage of transformer as a power transformer for any DC mobile charging application. We saw that the transformer operating at power frequency is bulky, so we should operate it on the switching frequency, which means that we should keep this transformer as a part of the converter. Now the analysis of transformer, which we saw till now in our basic BTech electrical thing, is operating using a by AC source. Now if you take example of any DC-DC converter, say a buck converter, and if we try to break the buck converter into two parts, so let's say here after the diode and this inductor, then we have to see that the voltage, so let's say we insert a transformer between it, so and this is the voltage across the diode. So this type of voltage has some average value with this. So if we add a circuit element between the diode and the inductance as an isolation, which is by addition of a transformer, which means that instead of giving a AC sinusoidal supply, we are giving a square supply or a square wave of zero average value. It should be zero average value, otherwise the inductance otherwise the transformer will be saturated, which means that instead of giving a sinusoidal component, we are giving a square wave component which has a harmonics of n order. We saw that the BH curve requirement, that in order to the transformer operating in both the modes. So here we saw that there are two regions of operation. Region 1 is the magnetizing region, region 2 is the demagnetizing region. So you can say that from zero magnetization or from zero residual flux, it starts magnetizing. Then if you increase the H or IM in the negative direction, or if you try to demagnetize the core, the B falls and then it goes in this fashion. Then again it increases and increases. So this happens multiple times. So let's say that we want to use a transformer in a switching converter. The switch is on, switch is off, on and off. Due to on and off action, the transformer BH curve, so basically it rapidly switches from region 1 to region 2 rapidly. And we are assuming that this BH curve is not changing its path. That is, this path, the discharging path and this charging path are almost constant by ignoring the non-idealities. That is, there is no loss during multiple cycles of what? Charging and discharging. This is only the initial path, assuming that there is no initial flux or the residual flux is zero. So what we saw, that we can apply the same principle of volt second balance which we applied to the inductor in a transformer. So we started with neglecting the non-idealities by analysis of the no load characteristics of a transformer, that if I2 I3 is 0, I1 equals to IM. So the average, so basically what happens is that the voltage across the LM, that is V1, should have zero average value. That is the volt second balance. So B is proportional to integral V1 dt and H is proportional to the current, and the slope of B versus H, which is nothing but mu, is also Lm. So mu is directly proportional to Lm. So if you want then we saw the condition for a transformer to operate as an inherent part of a DC-DC converter. The first condition is, which I already said, the volt second balance should be satisfied across the transformer primary side. That is, the average value of the transformer voltage should be 0 at the end of every cycle. And so in order to avoid the losses, the slope or Lm should be typically very high. Why? Is because if the slope is high, for less magnetizing current, the core gets more magnetic field density. The core gets more magnetic flux density. So that's why IM should be less, or XM or LM should be practically high. If XM is practically high, we can ignore that branch and we can directly say that I1 is I1 dash without any losses. And thus the volt second balance is IM is 1 by IM of t is 1 by LM integral 0 to t switching Vm of t dt plus IM of 0. IM of 0 is the residual flux. So the average value of Vm or V1 is 0. This is from equation number 2. We also saw that if volt second balance is not satisfied, the flux in the transformer core after end of every switching cycle will be more, or it will not be the same, which means that the core is continuously getting magnetized. It is not getting a chance to demagnetize. So this will result in the saturation of the core. So here we saw this will operate only at the end of this cycle, which means that whatever you increase H or whatever IM you increase, the B will remain the constant. That is, the core material is saturated. So to avoid that, the value of IM at the end of every switching cycle, except or ignoring the initial IM, should be same. That means the average value of IM should be constant. And now, considering the non-idealities, we have non-ideality as the leakage inductance. So the leakage inductance, we saw that it results in switching losses. But in some power converter, this leakage component is very much essential. For example, a dual active bridge or an isolated full bridge DC-DC converter, in that converter this leakage inductance is very important, and typically people try to reduce this leakage inductance in order to increase the power transfer capability of a isolated DC-DC full bridge converter, or a which is a dual active bridge. Dual active bridge is the name of a isolated DC-DC full bridge power converter. At the same time, so let's say you want to achieve zero voltage switching and zero current switching for a DC-DC converter. So in that case, the operating frequency of the converter has to be varied, which means that the switching frequency of the converter has to be varied. But if you want to make the switching frequency fixed, what you do is you vary the leakage inductance, or you change the leakage inductance based on the load. So that's why leakage inductance, which is inherent in a transformer or a DC transformer. So typically a transformer which we'll be discussing in the further lectures is the high frequency transformer, which is very small in size, very compact in size. It is also, it will be called as a high frequency transformer. So it is called as a high frequency transformer used in a DC-DC converter. So in the next lecture we will see the different types of DC-DC isolated converters, and the examples are forward converter, flyback converter, push-pull converter. In push-pull we can have push-pull full bridge and push-pull this thing, and then we have half bridge DC-DC converter, then we have full bridge DC-DC converter, then we have dual active bridge, and so on. So this we will discuss in the next class.